Now that we understand Agentic AI as an architecture, the next step is to build a clear mental model of the kinds of problems it can solve. So in this video, we will explore the product problem space. How to think about real-world problems in a way that makes Agentic AI relevant and powerful, and what types of products and companies are already shaping with it. This will help us understand where Agentic AI provides real value and how to design systems that take full advantage of its capabilities. An Agentic AI application is one that wraps around an LLM and uses it as its core source of raw intelligence. By building an agentic layer around it, the system applies that raw intelligence in a targeted, sophisticated, and reliable fashion to a specific problem, thereby creating an intelligent, autonomous solution. The mental model of AI as the new electricity is extremely on point. It's as if electricity has suddenly become available, and now the real questions are, how do we use it? What kinds of products can we build with it? Think about everyday appliances: refrigerators, microwaves, ovens, washing machines, televisions. Each one is a product wrapped around electricity, using its power to solve a specific problem. In the same way, we now have access to the raw, abstractive, intuitive intelligence of LLMs. And that means almost any software system can be reimagined as a product that wraps around AI, using it as a core capability to create intelligent solutions. Just as electricity powered a massive wave of innovation, LLMs and Agentic AI are powering a major transformation through the creation of new Agentic AI applications, which we often refer to as agents. This reimagination of software aligns closely with a powerful mental model introduced by Andrej Karpathy called Software 3.0. In Software 1.0, problems are solved using explicit logic written as computer code. If you want a computer to do something, you have to spell out every step of the process through programming. Then came Software 2.0, where instead of writing all rules by hand, we turn to machine learning. These systems learn patterns from data, and their behavior is encoded in learned parameters in statistical models. Now, in Software 3.0, we no longer write rules, and we no longer need to train task-specific machine learning models. Instead, we use large, general-purpose LLMs, and we program them with language. By simply describing the task, the constraints, or the desired outcome in natural language, the model can generate the solution. So a problem that once required explicit logic in Software 1.0 and later a trained ML model in Software 2.0 can now be solved in Software 3.0 by simply telling the LLM what we want. Let's take sentiment classification as an example problem. Deciding whether a piece of movie review text is of positive or negative sentiment. In Software 1.0, we would write explicit rules in code. For example, create a dictionary of positive and negative words, count which side appears more, and return the result. Every rule must be written by hand, and even small changes require rewriting logic. In Software 2.0, we stop writing rules and instead train a machine learning model. We collect thousands of positive and negative examples, encode them, and train a classifier. The learned parameters represent the rules, but we no longer write them. The model discovers them statistically, and now in Software 3.0, we don't write logic and we don't train a task-specific model. We simply describe the task to a large language model in natural language. You are a sentiment classifier. Here are examples. For each review, respond with positive or negative. With just a prompt, the LLM performs the task. So the same problem, sentiment classification, evolves from handwritten rules in 1.0 to learn the statistical models in 2.0 to natural language programming in 3.0. This is the shift happening across almost every software domain. Another useful mental model for understanding how agents can use LLMs comes from the early history of computing. Today, many LLMs are offered centrally, hosted in the cloud, and accessed via APIs. In this setup, agentic applications function almost like thin clients, lightweight systems that tap into a powerful remote intelligence. At the same time, we are also seeing increasing use of local models, smaller LLMs that run on personal machines or edge devices. Their performance may differ from large cloud models, but for narrow tasks, private environments, or offline use cases, a local model can be perfectly suitable. So the location of the model, remote or local, becomes an important part of system design. Both approaches already exist. A customer support agent calling a cloud LLM for high-quality reasoning, or a privacy-sensitive healthcare assistant running on-device using a local model. Each is valid depending on the product and its constraints. This mental model helps us see that agentic AI applications can be built in multiple ways, sometimes as thin clients accessing remote intelligence, and sometimes as systems powered locally or even combining both. Another useful way to think about the problem space is to remember what an LLM is fundamentally capable of. In the context of knowledge work, everything essentially boils down to producing or consuming information. LLMs can generate information, text, ideas, images, code, so we have the production bucket. LLMs can also understand, interpret, and analyze information, such as summarizing articles, reviewing documents, extracting key insights, which gives us the consumption bucket. These two buckets provide a clear mental model for positioning agentic AI applications. An agent that writes a blog post, drafts an email, or creates a report is in the production space. An agent that reads research papers, summarizes books, or analyzes meeting transcripts is in the consumption space. Some applications do both, but one side usually dominates depending on the problem being solved. And then there is a third bucket, orchestration. As more tools and models become available, we need systems that connect them, manage workflows, and coordinate tasks. This infrastructure layer is rapidly growing and is becoming its own category of value creation. So with these three buckets, production, consumption, and orchestration, we create a high-level map of where new agentic AI-related products are emerging and where value can be created in the knowledge work ecosystem. In summary, with the key ideas we have discussed, we can shape a strong and sophisticated product mindset, one that accelerates the creation and leadership of agentic AI products. First, we have LLMs as the source of intelligence. They provide the raw abstractive and intuitive intelligence that powers the agents. Second, we can think of agents as the counterparts of appliances. Just as appliances wrap around electricity to solve specific problems, agents wrap around LLMs to create targeted intelligent solutions. Third, we have the concept of software 3.0, software programmable with language. Instead of writing traditional code or training specialized models, we can now describe problems and goals directly in natural language. Fourth, we recognize the availability of intelligence in both remote and local form. Some agentic systems connect to centrally hosted LLMs, while others use local models, and both approaches are valuable, depending on the problem being solved. And finally, we see three major buckets in the problem space: production, consumption, and orchestration. These categories help us map where new products related to agentic AI are emerging and where opportunities for innovation and value creation exist. Together, these ideas give us a comprehensive perspective for understanding and designing agentic AI systems from architecture to application.